Hi, everyone. First of all, thanks very much for inviting me to do this webinar. And my name is Juan Alday, and I'm a postdoc at the Open University. And I've been part of the science team of one of the instruments on the TGO, the Atmospheric Chemistry Suite. And I've been working with that data for about 4 or 5 years now. So today I'm going to talk about some of the science topics that we are investigating with the instruments on the Trace Gas Orbiter. So first of all, I will be introducing and putting into context the atmosphere of Mars, and then I will be presenting the ExoMars Mission, and in particular the ExoMars Trace Gas Orbiter, and then I will go into the science topics that I've selected. There are the water cycle and the escape of water to space. Then I will talk about the isotopic composition of the Martian atmosphere as we measure it with the Trace Gas Orbiter, and then I will present the what we know about the newly discovered hydrogen chloride molecule in the atmosphere of Mars. So let's get started. Well, in order to put Mars into context, let's compare some of the planetary parameters with respect to Earth. And when we compare these, we actually find some similarities. So for example, if we look at the length of a day on Mars, it is about 24 hours as we do have on Earth. If we look at the planetary obliquity, so this is the tilt of the rotation axis with respect to the ecliptic, it is similar in both planets. So for the Earth, it's about 24 degrees, for Mars, 25 degrees. And this makes Mars experience 4 seasons as we do on Earth. However, as we do have some similarities, there are also some differences. So Mars is smaller, the gravity is lower, and also it orbits the sun at a larger distance than the Earth. So on the Earth, we orbit the sun at a mean distance of 1 astronomical unit. That mean distance for Mars is about 1.5 astronomical units. But also one difference is that the eccentricity of Mars orbit is higher, which means that the orbit is more elliptical. And essentially, the difference in the distances between perihelion when Mars is closer to the sun and aphelion when Mars is farther away from the sun, this difference is more pronounced on Mars than it is on Earth. And this is an important thing to note, because actually what we see with the Trace Gas Orbiter is that this change in the distance actually drives quite a lot of variations in the atmosphere. So we will get back to this. And then what about the atmosphere itself? Well, while on Earth, we've got an atmosphere with a surface pressure of 1 bar, which is filled mostly with nitrogen and oxygen. On Mars, the atmosphere is way thinner. The surface pressure is about 7 millibar, and it's filled mostly with carbon dioxide. So it's 96% carbon dioxide, followed by nitrogen, argon, and then a bunch of gases. And one important thing to note is that at the present conditions on Mars, with the current pressures and temperatures, liquid water cannot be sustained on the surface. So we see water, but we see it just in its vapor phase, so water vapor, and in its solid state, water ice. But liquid water cannot be sustained. But actually, has it always been like this? Well, there are numerous lines of evidence that suggest that liquid water was actually abundant on early Mars about 4 billion years ago. These lines of evidence include, for example, the geomorphological evidence. So this is when we look at the surface features, there are some features that resemble very much river valleys and lake basins, that they required a fluid to make them. But it is not only these surface features, but also when looking at the composition of the surface, a number of the so-called aqueous minerals have been detected, and these are minerals that require the presence of liquid water in order to be formed. But therefore, if I said that right now we cannot have liquid water, but there was liquid water 4 billion years ago, it must mean that the climate was different and the atmospheric properties were different. And if so, what has happened to the atmosphere? Has there been a transition from a warm and dense atmosphere to the dry and thin one that we observe today? Well, one of the hypotheses is that atmospheric escape has been substantial on Mars, and a substantial fraction of the atmosphere has escaped to space throughout history. And this is supported by the isotopic evidence. So the isotopic evidence, what suggests is that, well, when we look at the isotopic ratios in the atmosphere in different species like hydrogen, argon, carbon, nitrogen, oxygen, these are generally enriched in the heavy isotopes with respect to Earth. So the idea is that, well, the lighter isotopes, they are lighter, and when escape processes occur, these lighter isotopes can escape more easily than the heavier ones that tend to remain bound to the planet. And therefore, as the atmosphere escapes to space, the residue or the remaining atmosphere will be getting enriched in the heavy isotopes. But not only this isotopic evidence tell us that atmospheric loss has been substantial throughout history, but also if we couple this with evolution models, we can actually estimate the amount of atmosphere that has been lost to space. So here you have some estimates from the different isotopic ratios, for example. But making these kind of estimations about the amount of atmosphere that has been lost to space relies on some parameters. So we need information about the past and present isotopic ratios, and then about a parameter that is called the escape fractionation factor. So this escape fractionation factor, essentially what determines is how quickly the atmosphere gets enriched in the heavy isotopes when escape processes occur. And how this escape fractionation factor is calculated is by relating the isotopic ratios or the relative abundance of heavy and light isotopes in the escaping species in the upper atmosphere with respect to the relative abundance of heavy isotopes and light isotopes in the near surface atmosphere where most of the mass is. And not necessarily the isotopic ratios of the escaping species and the near surface ones need to be the same. There are some atmospheric processes taking place in the atmosphere that might alter these isotopic ratios. And precisely since with the Trace Gas Orbiter, we observe in this region of the atmosphere, can we say something about this alteration of the isotopic ratios? Well, so now that we've put the atmosphere of Mars into context, let me introduce the ExoMars mission. Well, so this mission emerged as a collaboration between the European Space Agency and the Russian Space Agency, Roscosmos, and it was developed as a two-stage mission. So first of all, the Trace Gas Orbiter and Schiaparelli, which is an entry descent module, were launched in 2016, and they arrived to the planet on the same year. Schiaparelli got released to the surface, and the Trace Gas Orbiter started an aerobraking phase until it reached its final circular orbit in 2018. And in March 2018, the Trace Gas Orbiter started science operations. And then the second part of the mission includes the Rosalind Franklin rover and a surface platform that right now they are awaiting a new launch date. But let's look into a bit more detail in the ExoMars Trace Gas Orbiter. Well, the payload includes 4 instruments. So there's CASIS, which is a high-resolution stereo camera designed to take high-resolution images of the surface. Then there's FRIEND, which is a neutron spectrometer whose main goal is to detect subsurface water. And then there are 2 suites of spectrometers, NOMAD and ACS. And I said that these are suites of spectrometers because they indeed include 3 spectrometers within themselves. So in the case of NOMAD, it has UVIS, which is a spectrometer measuring in the UV and the visible spectral range. And the main goal is to look at ozone and also at the aerosols in the atmosphere. Then there's LNO, which is an infrared spectrometer designed to take limb and nadir viewing observations. And then there's ESO, which is an infrared spectrometer designed to make solar occultations observations. And it is in these solar occultations observations that we try to retrieve trace gases and to measure the trace gases in the atmosphere. And in the case of ACS, the atmospheric chemistry suite, it also includes 3 spectrometers. So there's the near infrared, the middle infrared, and the thermal infrared spectrometers, tear beam. And I must say that here I selected some topics to go a bit into more detail into them. But there's a lot of science being done with the TGO, and right now there's a special issue on JGR that is the ExoMars Trace Gas Orbiter, 1 Martian Year of Science. So for people interested in the topic, I encourage you to have a look at this special issue because loads of the topics and the investigations that we are doing with the Trace Gas Orbiter are being published in this special issue. But one thing that we need to understand about the trace gas orbiter and why it is good at measuring trace gases is the kind of observations that it makes, that are the so-called solar occultation observations. So in order to illustrate how this works, I made a small animation. So here, well, what you can see, I took some profiles from the Mars climate database of as a function of altitude. So this is the pressure, the temperature, the volume mixing ratios of carbon dioxide in red and of water in blue, and then the dust abundance. And here you will be seeing the spectra that we measure with the instruments on the trace gas orbiter. So essentially what we do in this kind of observations, here the blue dot represents the trace gas orbiter. We are always pointing at the sun at all moments as we move along the orbit. And as we do so, the tangent point of the observation starts lowering down. And when this tangent point is at high altitudes, we essentially measure the solar spectrum because the atmosphere is very thin. But then as the tangent point starts going lower down, we start measuring the solar spectrum, but attenuated by the atmosphere. So we start observing some absorption features from different gases. So for example, here you can see the absorption features of carbon dioxide that are measured in the upper atmosphere. But as we start lowering down, we also start seeing the spectral signatures of other gases, for example, water vapor in this case, but this would also apply to other gases. And then as we start going lowering down, well, the dust starts appearing and it absorbs at all wavelengths, and there's a point in which the dust and the atmosphere is so opaque that we essentially can see no signal. But the idea with these observations is that we've taken a lot of measurements at different tangent altitudes. So when we use our radiative transfer codes and retrieval codes and we invert them all together, we can reconstruct the vertical profiles in the atmosphere. So that's one important feature about these solar occultation observations. And then why are these kind of observations good for measuring trace gases? Well, there are two main reasons. The first one is, as you can see here by this yellow line that represents the line of sight, we are always looking at the limb. And when we observe the limb, the air mass that we are observing is way higher than when we look at the nadir. That could be, for example, the white line in here. So looking directly to the surface. So this increased air mass and this increased line of sight density essentially means that we are more sensitive to the abundance of any gas, and in particular the trace gases. And the second reason why these kind of observations are good for measuring trace gases is because, as I said, we are always pointing at the sun and the sun is bright, and that yields high signal to noise ratio measurements, which is also ideal if we want to measure trace gases. So now that we've seen how the TGO takes its measurements, let's go to the science topics. So I'll start with the water cycle and the escape to space. Well, what did we know about the water cycle before of the arrival of the TGO? Well, most of the information that we had was about the column integrated column abundances. So here I took this plot. Well, I must say that these cycles have been measured by several missions. I took this plot from the paper of Trophimos-Key et al. 2015 using observations from SPICAM, the SPICAM instrument on Mars Express. And here what it shows is solar longitude. So this represents time and a full Martian year from 0 to 360. And then on the y-axis, you can see the latitude. So what we knew about the water cycle is that it's mostly controlled by the condensation sublimation cycles of water vapor onto the polar caps. So let's start, for example, with the aphelion season that coincides more or less with the summer season in the northern hemisphere. So during that season, what we observe is high abundances of water in the summer hemisphere, so in the northern hemisphere, because the polar caps sublimate the water, and that well, they release water vapor to the atmosphere. While for that same period in the winter hemisphere, the southern one, we observe low abundances of water because the water condenses onto the polar caps. So if we look now at the perihelion season, in which now it is summer on the southern hemisphere, the picture is similar but reversed. Now in the southern hemisphere, where we observe high water abundances, while in the northern hemisphere, where it's winter, we observe low water abundances because of the condensation onto the polar caps. So this is about the water cycle, and what did we know about the escape of water to space? Well, before, and here I need to note that when I mean water escape, actually the escape of water occurs in the form of escape from atomic hydrogen from the atmosphere. But as water is the main reservoir of hydrogen on Mars, they translate, but it actually occurs in the form of atomic hydrogen. And before, it was believed that water vapor was confined to the near surface atmosphere, so that most of the abundance of water was below 20 kilometers. At this altitude, water ice cloud form and water condenses, and basically that depletes water vapor above the cloud level, not being able to take the hydrogen to the upper atmosphere where it can escape to space. Instead, what it was suggested is that photochemical reactions in the lower atmosphere could produce molecular hydrogen, and this molecular hydrogen doesn't condense into the clouds. So it could rise up to the upper atmosphere where it could interact with CO2 plus ions, forming atomic hydrogen, and it is this atomic hydrogen that later on escapes to space. However, as the photochemical lifetime of molecular hydrogen is long on Mars, it is about 100 years. This is believed to give rise to a steady state escape of hydrogen from Mars. It is not expected to give rise to seasonal variations. However, recently, observations from the Hubble Space Telescope and Mars Express revealed some unexpected seasonal variations in the hydrogen density. These were first reported by Clark et al. 2014 and Chaffin et al. 2014, and I took this plot from Halekas et al. 2017, in which it shows, again, as a function of solar longitude, so for a full Martian year, the column density of atomic hydrogen in the upper atmosphere. And here it is highlighted where aphelion is and where perihelion is. So what it's observed is that the abundance of atomic hydrogen and the density of atomic hydrogen during perihelion is substantially larger than during aphelion. And this cannot be explained by this source of atomic hydrogen by molecular hydrogen. So instead, a new concept was suggested, that was that during perihelion, the atmosphere is dustier and the atmosphere is warmer. So these water ice clouds don't form at 20 kilometers. These water ice clouds form at 70 kilometers instead. And at 70 kilometers, the photolysis of water vapor can directly produce atomic hydrogen. And this atomic hydrogen can rise up to the upper atmosphere and can finally escape to space. So this was the concept that was suggested in order to explain these seasonal variations. But now with the Trace Gas Orbiter, we actually have information and we can measure the vertical structure of water vapor in the atmosphere of Mars. So what is it that we see, and can we say something about this? Well, in order to explain the climatology, I took this plot by this paper from Anna Fedorova et al. That has just been accepted in the JGR special issue, and this is using measurements from the near-infrared channel on ACS. This is kind of a busy plot, but I think that it summarizes quite well what we see about the vertical structure, the climatology of the vertical structure of water vapor. So here on the x-axis, you can see the solar longitude for 2 Martian years. So the second half of Martian year 34 till here, the full Martian year 35, and the first half of Martian year 36. And then on the y-axis, what you can see is the altitude for the temperature, water vapor mixing ratio, and the saturation ratio. And the left plots are for the northern hemisphere and the right ones are for the southern hemisphere. And then in this very top panel, what it shows is the latitude of the observations, because of the orbit constraints, the latitude of the solar occultations change throughout the mission. And what is it that we see then about the vertical structure? So let's start looking at the aphelion season when it's summer in the northern hemisphere, and that we measured it during Martian years 35 and 36. What is it that we observe? Well, we observe high water abundances. And well, here I must say that when I say high water abundances, they are indeed not high water abundances. So water vapor is a trace gas in the atmosphere, and it's in the order of parts per million. So it is relative high water abundances in terms of the seasonal variations. But we observe these high water abundances below approximately 20 kilometers. And at 20 kilometers, these water ice clouds form, and then the abundance of water drops drastically above this level. And this is quite consistent with the traditional scheme in which water was believed to be confined below 20 kilometers. And what is it that we observe in the southern hemisphere for this season? Well, it is a winter season during aphelion, and we observe very low abundances of water vapor, and the atmosphere is very dry. And then what is it that we observe during perihelion, when it's summer in the southern hemisphere now? Well, the picture is quite different. We observe high water abundances, but these are not confined below 20 kilometers. There are high water abundances up to 100 kilometers or even 120 kilometers. And not only we observe this in the summer hemisphere, so the southern hemisphere, but indeed the stronger circulation during this period actually transports water to the northern hemisphere as well, in which we can observe high water abundances, even though it's the winter season in this hemisphere. And one of the reasons why this high water vapor can rise to the upper atmosphere is the effect of supersaturation. So the effect of supersaturation was first measured by SPCAM on Mars Express. However, those measurements relied on not simultaneous measurements of water vapor and temperature that are required to measure the saturation ratio. But with the Trace Gas Orbiter, we can indeed measure simultaneously the temperature in the atmosphere and the water vapor. So we can derive the saturation ratio from simultaneous measurements. And what we observe is that supersaturation actually occurs throughout most of the year. And in particular, in this perihelion season, we observe high values of the saturation ratio that can exceed 10. So what this means is that the water ice cloud formation is not as efficient as it was previously thought, and therefore the hygropause or this water ice cloud layer is more porous than it was thought, and water vapor can go through it and can rise to the upper atmosphere, where it can produce hydrogen directly, atomic hydrogen. And now that we know about the vertical structure, can we say something about the escape of water to space? Well, one thing that we can do is to couple our TGO measurements with the photochemical model, and we can calculate the photolysis rates for water vapor in order to estimate the amount of atomic hydrogen that is produced in the atmosphere. So that is something that we did, and we did it for the different seasons and for all the observations. And what we found, it's shown in this plot, in which, again, it's solar longitude in the x-axis and the column integrated photolysis rate in the y-axis. And what we saw is that the photolysis rates during perihelion, they are about 2 orders of magnitude larger than during the aphelion season. And if we compare this with the seasonal trends of the atomic hydrogen in the upper atmosphere measured by the IUVS instrument on the MAVEN spacecraft that is shown here from this plot from the paper of Mayasi et al. 2022, we see that indeed these trends look very similar. So during aphelion, the abundance of atomic hydrogen in the upper atmosphere, it's low, and it peaks during perihelion. So this all suggests that indeed water vapor can be the main source of atomic hydrogen during the perihelion season and might be responsible for these seasonal variations. And then another topic that has been studied in quite a lot of detail is the impact of dust events in the escape of water to space. And in particular, there was a regional dust storm in 2019. And I think that this was quite special because different atmospheric properties were monitored by different spacecraft. So for example, I took this figure from the paper of Chaffin et al. 2021. And here in the lower panel, what you can see is that dust, as a function of time, the dust integrated column opacity as a function of latitude. So you can see that approximately on the 7th of January, the regional dust storm started, and it increased the dust opacity substantially. And at that very same time, the instruments on the Trace Gas Orbiter, so NOMAD and ACS, started seeing an increase in the water vapor at high altitudes, reaching altitudes of about 70 kilometers. And at that very same time, the IUVS instrument on the MAVEN spacecraft started seeing a brightening of the hydrogen corona that is typically used as a proxy for the escape of water to space. So this indeed suggests that all these atmospheric properties are related, and I think that they are giving us a good picture to understand how the escape of water to space works on Mars. But as you can see here in this, well, in the TGO data, because of some orbit constraints, there's a gap in which we missed part of the regional dust storm. So in order to estimate how the atmosphere looked like during that part of the storm, James Holmes and colleagues used a technique called data simulation, in which essentially what you do is to feed measurements to a GCM in order to constrain the GCM and get an optimal state for the model. So that's what they did. So here in these left panels, what you can see is the model outputs on top, and then the TGO measurements at the bottom, and you can see the TGO measurements from before the storm and after the storm, but there's this gap during the storm. So using this assimilation technique, they could estimate and get an optimal state for the model, describing how the atmosphere looked like during the storm, in which they could simulate the water vapor abundance. And also what they did is to actually take these assimilation reanalysis outputs and couple it with a 1D photochemical model that estimates the amount of the escape rates of atomic hydrogen from the atmosphere. And that is what you can see here in these black lines, in which the average is shown here as the red line. So in order to compare, or to estimate what the effect of the dust storm is, they compared it with the Martian year 30, in which there was not such a regional dust storm. And what you can see here is that indeed this kind of dust events can increase the escape rates of atomic hydrogen from Mars substantially. And as we were seeing before, these estimated escape rates, they actually correlate with a brightening of the hydrogen corona measured by the IUVS instrument on the MAVEN spacecraft. So it indeed seems that these kind of dust events are important in order to estimate the total amount of escape of water from Mars. So now we've looked at the water cycle and the escape of water to space, but with the Trace Gas Orbiter, we can not only measure the water vapor abundance, but we can indeed measure the isotopic composition of water vapor, and we can also measure the isotopes of other species. So as I was saying in the introduction, in order to estimate the amount of atmosphere that has been lost to space throughout history, we need to estimate the escape fractionation factor. And the escape fractionation factor can be modified or influenced by some different atmospheric processes. So what we are doing with the TGO is to measure the isotopic ratios of oxygen, carbon, and hydrogen in different species, like water vapor, carbon dioxide, or carbon monoxide. And we can see how these isotopic ratios are fractionated. So here you can see a summary figure of the isotopic ratios that we've been measuring with the Trace Gas Orbiter, but I'm going to go into a bit more detail about each of these isotopes. Well, in terms of the D2H ratio, what is it that we observe? Well, consistent with previous measurements, we observed that the Martian atmosphere is enriched in the heavy isotopes by a factor of 5 to 7 with respect to the Earth. And that is consistent with this hypothesis of substantial atmospheric loss and then the consequent enrichment of in the D2H ratio in the atmosphere. But not only we can measure that the D2H ratio is enriched in the heavy isotopes, but also we can measure drastic variations of the D2H ratio. And in order to explain the variations that we saw, I took this paper from the paper of Jerónimo Villanueva in 2022, in which I think it shows very nicely how the variations in the D2H ratio correlate with the variations in the water vapor abundance. So for example, here that it's shown the perihelion season in the southern hemisphere where it is summer, it shows that, well, water vapor abundances are high up to approximately 40 kilometers, and then the water vapor abundance, which is shown in blue, drops, and at that very same altitude, the D2H ratio also decreases. And if we go to the aphelion season, where it's summer in the northern hemisphere, and this season we saw that, well, water is confined below 20 kilometers. Indeed, we see this very drastic decrease in the water vapor abundance with altitude because of the formation of water ice clouds. But also we observe a very abrupt decrease of the D2H ratio. So why does this happen? Well, this is called condensation-induced fractionation. And this happens because the saturation vapor pressure of H2O and H2O is different. So essentially, H2O molecules condense a bit more efficiently than the H2O ones. So when water ice clouds form, the H2O condenses more efficiently and the D2H ratio in the atmosphere drops. And most of the observations that we observe in the D2H ratio, they are indeed consistent with this condensation-induced fractionation effect. Then what about the isotopes in carbon dioxide? Well, in this case, what we observed was a decrease of the heavy isotopes above approximately 100 kilometers. And why does this happen? Well, this happens because of the diffusive separation of the isotopes. So essentially, at the homopause, which is located on Mars at around 100 kilometers, the atmosphere transitions from a state of turbulent mixing in which, well, the atmosphere and the different species are uniformly mixed and they vary vertically according to the same scale height. That's the homosphere below the homopause, and above the homopause, we've got the heterosphere, in which molecular diffusion dominates, and molecular diffusion depends on the mass, and it will make the species very vertically according to their own scale height. And as the mass of the different isotopes is not the same, they are slightly different, we expect the heavy isotopes to decrease to decrease more abruptly than the lighter isotopes. So if we want to estimate what the fractionation of this effect is, we just need to actually ratio the densities of the heavy and light isotopes that is given by this formula in here. And in particular, we need to take into account their difference in mass. So one good thing that we can do in order to check whether this is the effect that is causing this decrease is to actually look at the relative fractionation between the oxygen isotopes and the carbon isotopes. This is because when we look at the oxygen isotopes, that's the oxygen 18 over oxygen 16. So the difference in mass here, it is 2. While if we look at the carbon isotopes, the difference in mass now, it's carbon 13, carbon 12, it's just 1. So we expect the variations in the carbon to be approximately half of the variations of the oxygen. So if we take the measurements above 100 kilometers and we make that correlation, we see that we indeed get this slope of 0.53 that indeed suggests that indeed it is this diffusive separation of the isotopes that is causing this decrease. And this is important because, as I said, in order to estimate the escape fractionation factor, we need to take into account all processes that fractionate the isotopes from the lower atmosphere to the upper atmosphere. And this diffusive separation, what we'll do is essentially create a depletion of the abundance of the heavy isotopes in the upper atmosphere where the escape processes occur. And then finally, we've been measuring the isotopic composition of carbon monoxide, and we've been comparing it with the isotopic composition of carbon dioxide. So here you can see some measurements of the carbon 13 over carbon 12 ratios and oxygen 18 over oxygen 16. And what we observe is that while for oxygen, the isotopic ratio is essentially consistent with the Earth-like value and pretty similar to the isotopic composition of oxygen in carbon dioxide, what we observe in the carbon isotopes is that it is depleted in the heavy isotopes. And why is this? So in order to understand why this depletion occurs, what we did is to look at the photochemical relation between CO2 and CO. And in particular, well, the reactions that control this relation are the same reactions that control the stability of CO2 in the atmosphere of Mars, indeed. So it starts with the photolysis of CO2 into carbon monoxide and atomic oxygen, and then there's the recombination of these species back into CO2. However, at first it was not well understood how CO2 could be stable in the Martian atmosphere, because the reaction rate of the recombination of the photolysis products, so CO plus O, this reaction is much slower than the photolysis. But then it was later realized that the stability of CO2 is instead controlled by reactions of carbon monoxide with the hydroxyl radical OH. And this reaction can recombine CO back into CO2 at a much faster rate. So what we did in order to explain this depletion in the carbon isotopes of carbon monoxide is to include this cycle into a photochemical model, but accounting for isotope effects. And in particular, the most important fractionation factor is the differential photolysis of the CO2 isotopes. So the cross-sections for the different isotopes are not the same, and in particular, they are larger for the main isotopologue, for the carbon-12 isotopologue. So that means that the photolysis of the carbon-12 isotopologue will be more efficiently, and we will be transferred more efficiently to carbon monoxide, producing a depletion in the isotopic ratio in carbon monoxide. That is what we observed with the Trace Gas Orbiter. So what we did is to include these isotope-specific reactions into the photochemical model and to estimate what the relative isotopic ratios in these two species are. So that's what you can see in this figure. So, well, here you can see the value of the isotopic ratio in carbon dioxide measured by the Curiosity rover. And then what the photochemical model predicts for this isotope is that it should be essentially constant until reaching 100 kilometers, in which it starts decreasing above that. And this is because of the diffusive separation of the isotopes that we saw before. And then for carbon monoxide, instead, this differential photolysis, what produces is a depletion of the heavy isotopes in carbon monoxide. That is actually in good agreement with the observations. And again, this is important because all these things, photochemistry, condensation, and the diffusive separation, they will all affect the relative abundance of the heavy isotopes and light isotopes in the upper atmosphere where the escape processes occur. So if we want to make accurate estimations about the amount of atmosphere that has been lost throughout history, we need to understand well how these processes work and how they affect the isotopic composition of the different species. And then finally, I'm going to talk about the newly discovered molecule hydrogen chloride. And I think that this is a very exciting topic because, well, the Trace Gas Orbiter was a mission designed to measure trace gases in the atmosphere. And this is the first discovery of the Trace Gas Orbiter of a new molecule, which I think is quite exciting. So in particular, hydrogen chloride is present on the atmospheres of Earth and Venus and plays an important role in their photochemical cycles. And on Mars, however, it had never been detected, and the abundances or the upper limits that were derived from previous measurements were actually very constraining. So even 0.6 ppb by the paper of Villanueva et al. 2013. But the presence of, well, there's chlorine on the surface, and the presence of chlorine in the atmosphere had also been suggested, for example, being sourced by active volcanism. However, it had never been detected. But now with the Trace Gas Orbiter and with the solar occultation observations, we've got this enhanced sensitivity to the trace gases, and we could detect this hydrogen chloride. So here what you can see is some transmission spectra at different altitudes. And in this transmission spectra, it is highlighted by these dashed lines where the position of the hydrogen chloride lines are. So these lines can be observed in different observations, so different solar occultation observations in different altitudes. So it's a very strong detection. And with this, using the different occultations and the different tangent altitudes, we can reconstruct also the vertical profiles. And what is it that we know about the hydrogen chloride now? Well, in order to look at the seasonal variations, I took this plot from the paper of Kevin Olsen et al. 2021, in which it shows, again, on the x-axis, solar longitude, so a full Martian year. And then for the lower panel, it is the abundance of HCl in the atmosphere. In blue, it's for Martian year 34, and in orange is for Martian year 35. And then in the top panel, it shows the column integrated optical depth, in which you can see here in blue, this high peak is due to the global dust storm in 2018. But what is it that we observe for HCl? Well, there are some drastic variations between the perihelion seasons in this side and the aphelion seasons on this side. So during perihelion, the abundances are higher. And again, I must say that when I mean high abundances are relative abundances, because these are found in the orders of parts per billion. So it's indeed very small abundances. But the abundances of hydrogen chloride peak during the perihelion season, and then they abruptly decrease when reaching aphelion, in which they are either low abundances or they are even below the detection limit of the instruments on the Trace Gas Orbiter. So from looking at these seasonal variations, what we can say is that they repeat every year, and therefore they are not caused by volcanism, because we would expect from volcanism to create these kind of seasonal variations. So instead, it could be some kind of surface dust atmosphere interactions that could be producing this chlorine in the atmosphere. In order to elucidate what the source and sinks of hydrogen chloride in the atmosphere could be, I took this paper from Shohei Aoki et al. 2021, in which it shows very nicely that the observations of water vapor and HCl are correlated. And indeed, the shape of the vertical profiles that we observe are very similar. So here you can see in blue the abundance of water vapor for different observations and the abundance of hydrogen chloride in orange in here. So when you look at the correlation between these are indeed correlated. So then what we are seeing is a correlation between water vapor, dust in the atmosphere, because it happens during perihelion, and then the abundance of hydrogen chloride. So the hypothesis is that probably the source of HCl in the atmosphere of Mars might be the hydration of chloride salts, like sodium chloride, that they could release chloride radicals into the atmosphere and then finally form HCl. That is the main reservoir of chlorine in the atmosphere of Mars. And then one thing that is not well understood either is the rapid decrease that occurs in the atmosphere between the perihelion and aphelion seasons. So the photochemical lifetime of HCl is longer than that, and it is not expected to give rise to such seasonal variations. So instead, we need another unidentified sink. For example, this striking similarity between the profiles of H2O and HCl, in which we see this abrupt decrease of the abundance, could suggest that it is uptake of HCl by water ice clouds. However, it is not clear yet whether that's the actual process. It could be also heterogeneous processes in which chlorine comes back to the dust particles or to the surface. So I think that this is a topic with a lot of questions to answer, but I think that precisely makes it a very interesting and exciting topic to study. And now I will leave the conclusions here. So, well, with the Trace Gas Orbiter has been operating now for about 4 or 5 years, and it has been providing unprecedented detail on the vertical structure of different atmospheric parameters. Here I just talked about 3 topics that I selected, but there's a lot of science being done with the instruments on the Trace Gas Orbiter. And there's a special issue on JGR that I encourage you to have a look, because there's very interesting science being done with this mission. Then about the 3 topics that I introduced today, well, about water vapor, the take-home message is that we find drastic variations between the perihelion and aphelion seasons. And in particular, during perihelion and during dust storms, what we see is that water vapor can reach the middle and upper atmospheres of Mars, allowing a direct production of atomic hydrogen that potentially increases the escape rates of water to space. In terms of the isotopic ratios, we are monitoring the isotopes in different species, and we are seeing that indeed these isotopic ratios vary and are altered because of different atmospheric processes such as condensation, transport, and photochemistry. And it is important to take into account these processes if we want to make accurate estimations of the long-term evolution of the Martian atmosphere. And finally, the TGO discovered a new molecule on the atmosphere of Mars, hydrogen chloride, and I think that's very exciting, and it reveals a new chlorine cycle on Mars. The source of this chlorine, it appears not to be volcanism, but rather some dust-atmosphere interactions. But this is a topic that is under investigation now, and I think that it's a very exciting topic to study. And I will leave it here. Thank you very much for listening, and I will take any questions.